We've previously discussed what the basis of a vector space is. It's a linearly independent set that spans the space. So, to show a set of vectors is a basis for a vector space, you have to prove those two things, that it's linearly independent and that it spans the space. But now that we understand also what the dimension of a vector space is, there are some quick ways we can determine if a set is a basis in certain examples. Links in the description to my lessons introducing bases and dimensions if you need to review. Here's an example. Do these two vectors form a basis for r squared? Well, we know that the dimension of r squared is 2, so we certainly have enough vectors here to form a basis. The question would be, are the vectors linearly independent? If these two vectors are linearly independent, then we know that it has to be a basis, because that's the dimension, it's 2. Two linearly independent vectors in r squared would be a basis. And since these are only two vectors, it's very easy to check that yes, they are linearly independent. If they weren't linearly independent, then v2 would have to be a scalar multiple of v1, in which case v2 would have to be 2 times v1. That way, the 5 would get multiplied by 2 to match the 10. But we see that doesn't work because -1 times 2 wouldn't give us the -3. So they're not scalar multiples of each other, so they are linearly independent. Since we have two linearly independent vectors, and the dimension of r squared is 2, this does indeed form a basis. v1 and v2 aren't scalar multiples of each other, so they form a linearly independent set, and since that's two vectors, which matches the dimension of the space, this set is a basis for r squared. We can also sometimes use this sort of shortcut in r cubed. Do these three vectors form a basis for r cubed? Well, the dimension of r cubed is 3. So if the three vectors are linearly independent, then yes, indeed, they form a basis. But in this case, there's 3 of them, so it's not as easy as just checking if one's a scalar multiple of the other. But at a glance, we can see that v1 and v2 both lie in the yz plane, because they both have 0 as x-coordinates. So they're in the yz plane. Are they linearly independent? Are v1 and v2 linearly independent? The answer is yes, because, for example, you'd have to multiply v1 by 5 to get the 1 to match up with the 5, but 3 times 5 is not 7. So these are two vectors that lie in the yz plane, and they're linearly independent. Throw in this third vector, v3. Are the three vectors linearly independent? We can easily say that yes, they are, because if they weren't, then v3 would lie in the same plane as v1 and v2, the yz plane. But clearly, v3 does not lie in that plane because its x-coordinate is -5. So it can't be in the yz plane. So we have that v1 and v2 aren't scalar multiples of each other, although they do both lie in the yz plane. Meanwhile, v3 doesn't lie in the yz plane. So yeah, these three vectors are linearly independent, and so they form a basis for r cubed. 3 linearly independent vectors will form a basis for a dimension 3 space. And again, the idea is we're trying to do this more or less by inspection, without busting out Gauss-Jordan elimination or systems of equations. Sometimes it's possible to just look closely at the vectors and the vector space in question to determine if you have a basis or not. One more example. Do the vectors p1 and p2 seen here form a basis for p1, the vector space of polynomials with degree at most n? Well, the dimension of that vector space, p1, is 2, and we do have two vectors. So if these two vectors are linearly independent, then yes, together they form a basis. However, we see that they are not linearly independent because p2 is equal to -2 times p1. You can see that -2 times 1 would give us that -2, and -2 times -x would give us that plus 2x. So no, not a basis. The dimension of p1 is 2, so we would need two linearly independent vectors, and we don't have that because p2 is a scalar multiple of p1. So that is not a basis. So those are a few examples of how we can use our understanding of the dimension of a vector space to quickly determine in certain cases if a set of vectors is a basis for the space or not. Let me know in the comments if you have any questions, and be sure to check out my Linear Algebra course and Linear Algebra exercises playlists in the description for more. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about.